Hello? Okay. Hello, everybody. Please continue enjoying your lunch, or if you haven't got it yet, please get it. We're going to continue with our program here. But one housekeeping note, we are going to be drawing for the prizes from those passports at 12:30, right after our speaker is done. And so you have about a half an hour to get into the exhibit hall and finish getting your signatures on your passports and getting them turned in. Because right after the speaker's done, we will draw for these prizes that are up here. And so we have a lot of good prizes, so make sure that's filled out and turned in. So, without further ado, let's move on to our lunch speaker. And today our lunch speaker is Mr. Mike Armstrong. He's the Business Development Manager for Solar Energy Division, Soltech. Mike Armstrong is the primary business development manager for utility scale projects for Soltech Solar USA. He has worked with Soltech Solar for nearly 4 years and has been part of the U.S. development team since its inception in 2009. His responsibilities have been primarily focused on business and project development with the California utilities. He has been involved in nearly all aspects of the strategic business model that Soltech has implemented for the U.S., and he has been closely involved with the development of Soltech's 155 megawatt of projects with SDG&E. So help me in welcoming our lunch speaker, Mike Armstrong.
Connor, how do I work this? Good afternoon, and thank you for joining me for a brief tour of Soitec. Just to give you an overview of what we are, we're a locally based manufacturer. So we have a manufacturing plant in San Diego, and it's in a little northern community called Rancho Bernardo. That's kind of an interesting position for an American company to be in. There aren't many American solar module manufacturers left, and we got in while everybody else was getting out. And that philosophy, that decision was made in 2010 after we'd been here for about a year. And we decided that we were going to invest in the U.S. and we were going to develop in the U.S., which means that we're a vertically integrated manufacturer, just like for solar. So, a little background on what Soitec is. We're a semiconductor manufacturer. We're based out of Bernin, France, and we make solar cells, we make diodes, and we make semiconductor materials. So we were founded about 20 years ago. We make about $450 million a year, listed on the European Stock Exchange. And currently, we have locations, factories, sites in about 17 countries. Worldwide, we have 1,500 employees. The patent portfolio is enormous. And some of the major clients we have here in the US for the semiconductor side is IBM, AMD, and large value-added manufacturers in the semiconductor chip to board sector, which means that they're selling to Apple, to Qualcomm, to the keyboard manufacturers and the game manufacturers. Why that's important? It gives us as a solar developer a large parent company that can stay with us and help us develop. Oops. So the origin of the company that Soitec acquired 3 years ago was in Freiburg, Germany. And we're a spin-off from the Fraunhofer Institute, which is very similar to kind of a combination between NRIL and Caltech. The manufacturing facility that we have in Rancho Bernardo currently can turn out about 140 megawatts a year, and the manufacturing facility in Germany is about 70 megawatts a year. I would invite any of you to come and visit the factory. We'll be happy to take you on a tour. And one of the things you'll notice is there aren't many people working there for the size of the factory. It's about 160,000 square feet. And currently we have about 150 employees. Once we put the other line into manufacturing and we go into 3 shifts, we'll be up to about 400 employees. Most of the work is done by robots. And the people that work there maintain the robots, program the robots, repair the robots. When they break, get them back online. From a solar perspective, these are the key locations for Soitec Solar, which is one of the divisions within Soitec Semiconductor. 2 locations here on the West Coast, and then 4 locations in Europe, 1 location in South Africa. The technology itself was originally created not for solar power plants, not terrestrial ones. It was originally created for satellites. What they found was about 20 years ago that the satellites' silicon solar cells didn't hold up well to the harsh conditions of space. Heating, cooling, degradation rates were quite high. So they created the 3.5 semiconductor cell. And the interesting thing about the cell is it's very resistant to heat degradation. What that means is you heat up a cell, it tends to lose its ability to transmit electrons. And with the 3.5 semiconductors, that isn't the case. What that cell looks like, if you were to look at it under a microscope, it's 27 layers. 3 layers capture different wavelengths of light. So it's very efficient. It's more efficient than any other solar cell out there. From a strictly manufacturing standpoint, it's easy to make. The module itself, the chip is 3 millimeters across. The module is enormous. So you have very few chips. You have 200 chips on a module and 200 magnifying glasses. And those Fresnel lenses, those magnifying glasses, create a 500 to 1 power ratio. So they get 500 suns onto one little dot. It creates an enormous amount of heat, but it creates an enormous amount of electricity as well. The example of the module that you're looking at down here is approximately a 29 kilowatt module. The dual access track module in that photograph is of the one that's up at UCSD in San Diego. The technology in comparison to the other technologies, which you all see out here in the Imperial Valley, is thin film, silicon, best-in-class silicon, and then the CPV technology. The basic advantage that CPV has over the other technologies is not that it's so much better right now, is that it's on a bench test basis, it's at about 43.7% efficient. So 43% of the photons that hit that get turned into electricity. The physics tells us that that can go well into the 50% range and be commercially viable. And that's much better, has much more headroom than your other technologies of thin film and of silicon. One of the interesting things, though, is that First Solar was able to, in a laboratory environment, recently set a record, I believe, for thin film. They were up in the 18% range, which was very encouraging for them. But the thing to remember about the Soitec technology is 5 years from now, we won't be at 37%, we won't be at 38%, we'll be at 47, 48, getting up into the 50% range. And that's what makes the technology so exciting, is that you really have a lot of distance in front of you that you can improve and, just very important at this time of the market, be able to compete against the other technologies and get into those low PPA price range. Now, one of the interesting factors and one of the challenges of CPV is it only takes direct light. So the DNI is quite important. And the areas that you see here that are in yellow, the bright yellow, are the regions that this technology works best in. It won't work at all in areas where you have lots of overcast. Any amount of cloud cover does create a problem for the technology. But currently we've got either test sites or power plants in every continent, and even in Chile, in South Africa, North Africa, China. I believe my European counterparts are putting in a prototype in Australia. That's the last continent that we're not on. From a developer standpoint, there's some real interesting characteristics of the cell. Water consumption only occurs during construction and cleaning. And as far as cleaning is concerned, we use a robotic device and steam so that you can clean about 1,000 square feet for about 3 to 4 gallons. Low degradation factors of the multi-junction cell, which means not heat degradation, but actual cell degradation. You put something out in the sun for a long period of time, and it does begin to have an effect. And some of the other technologies are more affected by degradation than we are. Currently, the degradation that we're experiencing in the test modules that we have at NREL are insignificant. They're way below anybody else's degradation. And to some extent, it's actually difficult to measure, which makes it difficult to actually write a warranty for, because you have to actually assume a degradation that you can't prove, because you can't measure the degradation. So we basically assume a number above that's rational, and that's what we warranty for. The glass itself is very durable. It doesn't tend to scratch. The test modules that we've had in Spain, North Africa are still doing quite well. Wind is obviously a consideration. Some of the areas that we're in, well, any desert that you develop in has wind. And the module field has an automated system whereby it senses the wind, and if a wind gust or a steady wind exists for a longer period, I think it's 3 to 5 minutes, the whole field goes into stow. So it just stows itself and waits to measure the wind automatically in the next 15-minute increments, and then the system goes back into production. One of the advantages we have, and one of the points that attracted a great deal of attention among the IOUs was we were able to stay in production during those peak hours where the utilities really needed the power. In the summertime, the date that I've been given is August 19th at 4 o'clock in the afternoon. That's when they need the power. And the wonderful thing about dual access tracking is that August 19th at 4 o'clock in the afternoon, it's still pointed straight at the sun, and it's at 90% production. The blue curve is the curve that we particularly have. The brown curve is your standard PV, and then the mustard-colored curve above is your utility power demand. And the dual-axis tracking systems are ideal for this, just as the single-axis tracking. You noticed that recently most of your silicon power plants are taking a hard look at single-axis tracking to be able to address this issue. The production sites and the test sites that we have reassured us and given us some guidance on the scalability of the technology. In some areas, it's as simple as drilling a hole, 28-inch diameter hole, driving a mast in the ground, and then trenching the cables to the mast. It's really that simple. Other areas, which is even better, is you just vibrate the mast into the ground. You can literally put a mast up in 15 minutes. Putting the module bed on it is a little bit more of a process, but as far as getting the field itself developed initially, it's a very quick process, providing the geotechnical cooperates with you. We've had, the interesting thing is we've had modules in the field for a period of about 8 years now. First of those modules went in the field as individual modules at test stations. I believe NREL has several of the modules. We've got a couple of them at a test center in Spain. And then we have a couple of test power plants, very small power plants, about 500 kilowatt plants in Spain as well. The biggest plant we have right now in the United States is approximately, it's a little bit over a megawatt, and it's at a molybdenum mine in Cuesta, New Mexico. And this power plant was bought by Chevron Technologies, and they installed it. It's been in operation now since about February or March of 2011. The interesting thing was I was there for the dedication, and the wind started picking up, and just at the wrong moment when all the cameras were pointed at the field, it went into stow. But right on schedule, 15 minutes later, it went right back into tracking. So we sat there with all the media and went, wait. You know, the reason why we located in the U.S. Southwest for the Soitec Solar was it's intuitively obvious to us, but it's not always obvious to everybody else. High DNI, growing electricity demand. You want to be close to those load centers that you can service. The renewable portfolio standard, the political support was tremendous. And the growing infrastructure. We've seen several of the panelists describe what they're planning on doing to address some of the choke points that we currently have to deal with. We're fully confident that in 5 years' time, we're going to be able to develop and deliver power in areas that we wouldn't even look at right now because of the constraints. Another reason why we're here is the Sunrise Power Link. We were able to, a quick story about this. Early in 2010, I was asked to help put together a team to go evaluate all of the states in the Southwest as to where we wanted to put our factory. And it was never really a really warm welcome. It was always a bit of a struggle. And I met with the governor's offices of all the Southwest states and their utilities. And it wasn't until we came back to San Diego and we connected with Tim Kelly's counterparts in San Diego. And then they connected us with Cleantech San Diego, the mayor's office. And the first meeting we had with the mayor was at the boardroom of SDG&E. And we said, we'd like to bring a factory. We need help with PPAs so that we can feed the factory. And at about that point in all the other states, things got real slow. And at the meeting we had at SDG&E, Jesse Knight, who's head of SDG&E, was sitting at the head of the table, and right next to him was Mayor Sanders. And right down the table from him was Jim Avery. So we described what we wanted to do, and Jim Avery stood up and said, I think we can do this. And it's been, it hasn't been easy, but we have a factory now. We have 305 megawatts of signed PPAs approved by the CPUC, 150 of which are going to be here in Imperial Valley. And we're working on another 150 for the Imperial Valley. So it's been a terrific experience, and it's all because of the Sunrise Power Line and SDG&E. They've been very, very helpful. I haven't actually seen this presentation before. It got mailed to me last night at 10:30. This is my point exactly. So we've been able to really have a good relationship with the city and the utility. And if you'll notice, the gentleman here on the right is the founder of Soitec. The next gentleman over is the Dean of Engineering for UCSD. The next gentleman over is the Mayor of San Diego. That's Jim Avery. Off his shoulder is you can see. Off her shoulder is Cleantech San Diego. And they all showed up for the announcement that we had struck a deal with Tenaska. This is a video that was, the reason I only got this last night was this is the video that they inserted. So we'll be seeing it together. Connor? I think you have to push the button. Oh, cool. Don't you love technology?
Soitec is a 20 years old company. I founded this company in 1992. We are publicly listed since 1999.
We have 1,600 people globally. We operate 6 factories around the world. Our CPV modules are designed to have 2 to 3 times higher efficiency than traditional solar panels. They're also mounted on 2-axis tracking systems, so they follow the sun from morning to night and generate energy for the utility when it's needed most. Our solar cells used in our modules have an efficiency of 38%. And Soitec has proprietary technology to improve that efficiency. Our technology has been field proven around the world globally in bright and sunny locations like the desert Southwest, and we have a track record approaching 7 years at this point.
I think the track record we have on the field, the technology which is backed today by independent engineering studies, I think all of that shows that this technology today has reached the maturity level to scale up in the hundreds of megawatts.
This factory was built to support over 300 megawatts of power purchase agreements with SDG&E using this technology.
Soitec is going to manufacture solar panels right here in San Diego, producing local jobs, and those panels are going to be used to generate electricity that'll be consumed here in San Diego.
The modules we manufacture in this facility are very simple. They're made of commodity materials like glass and aluminum, and they're meant to be durable and last 25 years. So our Soitec CPV technologies is one of the most cost-effective way of making solar electricity in bright and sunny locations like the desert Southwest.
We're very proud of the fact that we're a leader in the development of CPV, concentrating photovoltaics, and Soitec is a leader in the production of CPV panels.
Thank you, Connor. So as the dialogue from Clark points out, is the factory is designed for 280 megawatt peak production, and employs about 450 people. And it's a balance sheet investment for Soitec of $150 million. The building that we occupy is the old Sony manufacturing building, and we purchased that outright about a year and a half ago. Recently, we were awarded a SunPath grant, and I believe it was the grant was $25 million, for which some of that goes toward our factory. It was a grant because we had done a terrific job of bringing the assets and building the factory here in San Diego, and then interacting with the DOE and the DOD for projects that we're going to be working on with them. And as part of that process, we were asked to submit for the grant, and lo and behold, we got it. It's actually a really interesting concept. This is where the government is really important in that they're trying to encourage unique and innovative businesses. And I think we're certainly that. And that concludes the talk. But before I leave the stage, I'd like to share a couple of observations that over the last 4 years, we've obviously been very involved in Imperial Valley because of Tenaska and because of other interests that we're trying to develop out here. And this is a plug for Tim Kelly. Yay, Tim! Tim's office has been just awesome. Very, very helpful. We've been very fortunate to hook up with him and be able to use his resources, and I thank him for that. The other interesting thing, a little story, is that there's a very long phone line between here and France and Germany, and trying to convince them why Imperial Valley is important was originally a bit of a challenge, but with the Sunrise Power Link being here and Tenaska being here, that was okay. That was a good reason. And I said, no, you don't get it. This is the renewable center of the world. And you'd hear this long silence, and they go, well, how many megawatts? I went, no, think gigawatts. Think wind, geothermal, solar, biomass. Think about all of it, hydro. And they've slowly come around, and they really begin to understand and appreciate how important Imperial Valley is. And I've had conversations with people in San Diego that don't get it. They don't understand why. Why the Sunrise Power Link? Why Imperial Valley? And I think slowly it's really beginning to, it used to be that nobody understood, and now at least 10 people in San Diego understand why it's important. But it's getting better. Thank you very much. I'll be glad to take any questions if you have them, either here on the stage or yes, sir.
You had mentioned that when the wind blows, they'll shut down.
Yeah.
What's wind speed causes them to shut down? Is it 10 miles an hour, 100 miles an hour, 1,000 miles an hour?
Good question. They're designed to withstand hurricane force winds, but what happens is you begin to lose the focus as the wind begins to climb, and you can also experience structural damage. You know, if you get a tracker in the upright position during a high wind. A little side story is Germany was working on one of our trackers up at UCSD when we had a very significant wind event on the coast. Gusts above 60 miles an hour, sustained wind in the 40 mile an hour range a couple years ago. And I'm standing next to the tracker at 2 o'clock in the morning on the phone with Germany going, please put it into stow. And the tracker was definitely, you saw an inch or two movement on it, but that was it. And they did not put it into stow. They were doing some software upgrades and they couldn't. There is a 9-hour difference between us and Germany, so things happen in the middle of the night here. They're working on it there. But to get back to your question, the stow speed is entirely programmable. Depends on what you want, depends on what the geotech of the area indicates. If you're planting trackers in solid rock, your wind stow speed can be higher. If you're in alluvial sands, you're going to want a lower track speed because that tracker is like a sail. The torque on that is going to be significant if it gets stuck in an upright position. So normally it's about 30 miles an hour.
You mentioned that first I should say that's very impressive efficiency numbers. That's quite something. You mentioned that the system generates heat, presumably from concentrating from the Fresnel lens. And my question is, how hot does it get at the glass? And if somebody were to want to install a, say, water cooling system behind the glass, would that be beneficial or detrimental to your process?
First question is, the heat is dissipated by what we call a heat spreader. It's a little piece of a square piece of aluminum about 2 or 3 centimeters across. And you can, during the height of the day, you know, at 1 o'clock in the afternoon, you can put your hand on the back plate of a tracker, and it's hot, but it's not going to burn you. So that kind of gives you a feel for it. We actually have looked at 2 possibilities as far as having some sort of an auxiliary benefit from the tracker, hot water being one of them. Also putting other types of solar technology behind the plate because light does pass through. The problem is that you then have to have a heavier tracker structure. The economics begin to become less decisive. And the German company, Concentric Solar, who designed this, looked at all sorts of possibilities and decided that they would stick to their knitting and create the perfect tracker for CPV and not worry about the other possibilities.
Can we know the materials for the 3 junctions you use? You said you can convert light from 3 different wavelengths?
Yes.
So you need 3 band gaps, so the materials for each of them, can we know that?
Yes, actually you can. You can know what every material is in the cell.
Yeah.
The cells are made by Solar Junction up in Silicon Valley. They're made by Azure, MCore, Boeing Spectra Labs. And we use, although we're trying to manufacture, getting to the point of manufacturing our own cells, we are still using one of those other manufacturers' cells.
Okay.
And very shortly, we'll be in a position to manufacture our own. But you can go onto each one of those websites, and they'll tell you exactly what's in their cells. They have to disclose, it's important to disclose that.
Thank you.
Okay.
That's smart. You mentioned that you're going to be building a project here in Imperial County, and I was wondering if, as you ramp up on that project, you'll be prioritizing a local workforce.
Oh, absolutely. It's the reason, that's actually an easy answer. I mean, we were encouraged to put our factory in Mexico, in Nevada, any place, literally, their consultants, what do they describe? It's any place but California. Literally, that's what they said, any place but California, don't do it there. The reason why we built in California was obviously the Sunrise Power Link, SDG&E, but it was also you had a talented and capable workforce. So that's why we're here, and we're not going to change that. Taxes, number one, difficulties in meeting environmental guidelines. There was a number, I mean, they had a whole list, and then we ranked them in importance compared to the PPAs, compared to the workforce, any number of other criteria within that matrix. And it became a pretty clear, at least from our point of view, a pretty clear or easy decision that San Diego was a good choice. Thank you.
I want to thank Mike and Soitec for their sponsorship and their participation and coming down the Imperial Valley. And I also want to apologize to Mike, to you and your company for mispronouncing the company name when I started. That comes from old age and the brain and the eyes not working correctly, so I apologize. Okay, now's the time a lot of you have been waiting for. It's prize time. Terry, you coming up here to help me? First thing we're going to be giving away are these plants in the front here. And so you get 2 plants. It's either 2 desert agave or 2 buckhorn cholas? Choya. Okay. My Spanish is not that good either. So the first person gets to pick which one, and the second person will get what's the other 2. And these are plants native to the Imperial Valley, and Recon collected seed and grew plants in native plant nursery. No, go ahead. Yeah, give it to somebody to draw, and that way they don't think I can't win anyway. Now, hopefully I can read the name. Okay, let's see. First one, Ned Batishi. Ned Batishi. There we go. So come on up and pick which one you want, either the agave or the buckhorn choya. You got 2. Yeah, there you go. Take those. Those are yours. Congratulations. You take 2 of them. You get both of them, so you can put them on one side of the house or the other, whatever you want to do. This is a new landscaping plan. Okay. Yes, give them a hand. Congratulations. Okay, so we have the other 2 plants left. That'll be next. And these you have to be careful with. Make sure that you don't sit on them. Peter Fisher. Peter Fisher. Now you can always remember the Imperial Valley. When you're away from here, you can remember the... Those are yours. You can give them to your enemies if you want. It's not so... There you go. Congratulations. Okay, now, moving on, the next one is from Soitec, as a matter of fact, our speakers company. It's a solar charger. Okay, and the name we have here is Lydia Alvarez. Lydia Alvarez. Is Lydia here? Okay, we'll put this over here. Up here. Okay, the next one is a gift basket from Rabobank. It's like the Academy Awards opening these. Jerry Buckowitz. Is Jerry still here? No? We can get that to Jerry. Right. Yeah. Does it say we have to be present? Okay, must be present to win. Yes, okay. So next one. Okay, Matt Desert. Yeah. Speech. Pays to be present. Yeah. Okay, the next one is a $50 burgers and beer gift card from Tenasca Solar Ventures. And that is Francisco Cachu. Cachu? Which was that? It's just a card. There we go. Thank you. Okay, the next one is an energy efficiency kit. Thank you. From the IID. And that goes to John Phantom. Oh, we got a lucky table over there. Yep. Okay, the next one. And we're getting to these ones you've been waiting for. A Kindle Fire from Lewis, Brisbois, Bisgard, and Smith, LLP. And the winner is, oh my God, Gary Wyatt. He always gets in with the attorneys, you know, it's just... Congratulations. Okay, now, we have got 2 iPad minis up here. And the first one is from the Passports, and that's from the Imperial Valley Economic Development Corporation. And that goes to Patricia Valenzuela. Now we know that you're going to use that to get projects going a lot faster. Great, thank you. Congratulations. Okay, and then Rabobank had a separate drawing at their booth, and the winner of this iPad mini is John Hernandez. All right. Okay, I think that's all the prizes, and thank you everybody for visiting all the booths and taking care of that. And congratulations to all the winners. Okay, we'll move right on into our our next industry-specific Session 2, Geothermal 101 and Exploration. And the moderator for this is Gene, I don't know if I can pronounce your name properly, Sumnicht. He's the CEO and principal for EGS Incorporated. Gene is the CEO and one of the principals of EGS Incorporated, a geothermal consulting firm. He has more than 35 years of professional experience in geothermal exploration and development. His background includes extensive work in geology, geochemistry, and geophysics. He was directly responsible for the geologic planning for more than 350 megawatts of development and makeup drilling in the geysers and 250 megawatts in the Salton Sea. Heber and Brawley fields for Unocal Geothermal. He has been the project manager or chief geologist for diverse geothermal exploration programs throughout North America, Central and South America. This goes on. Europe, the Middle East, and Asia. You've been all over. He has been the principal investigator for DOE-funded research and technology development programs in enhanced geothermal system experiments in the Brady and Desert Peak fields in Nevada. He has done due diligence for more than $1 billion in geothermal asset sales, ownership transfers, and refinancing during the last 2 decades. He was the exploration and development manager for Ormat Technologies until becoming chief geologist for EGS Incorporated, where his responsibilities included assessing geothermal resource areas in the United States, Central, South America, and Asia. So please help me welcome the moderator for this program. Oh, we change? Is there, oh, okay. And so, Charlene, come on up. Charlene Wardlow from Ormat.
So the Geothermal Resources Council, which is a 501c3 organization and is mission is education of geothermal energy around the world. We're a world organization. We have about 1,700 members from around the world, and we focus primarily on technology, science, and education. And we have an annual meeting every year that brings in people from all over the world, and part of that is also the Geothermal Energy Association trade show, and they're a 501c6. They're kind of our sister organization based in DC. The GRC is actually based in Davis, California. And I hope you got to see our table here. Ian Crawford taking the pictures was here along with Brian. And they've got a couple little things up there in the back. Our GRC annual meeting will be in Las Vegas this year. We've never done that venue. We'll be at the MGM Grand the first week in October and hope you'll come and join us. We have geology field trips. It is only 6 hours from Vegas down to Imperial County, so they'll probably have field trips down here for the geology as well as power plant tours, either there or Tocoso or Mammoth Lakes, where there's a project there at Mammoth that Ormat owns. So the GRC was asked to help sponsor this Geothermal 101 class, and I've worked with Gene on a lot of different projects from Northern to Southern California, and appreciate his expertise so much. You will learn a lot. I've used him in a lot of other programs to help educate people, and I know I will learn a lot more about the geology of this area. And I really got to thinking, we're here to talk about the geology as it pertains to geothermal energy, but really the geology is why we have renewable energy here in the valley. It is because of this basin that we have wind on the west side of the valley. It is because of this basin that we have such high solar potential. And it's because of this basin that we have the Salton Sea with the San Andreas running right down through it. So even though we're talking about geothermal energy, it is the geology that has provided the Imperial Valley, the Colorado River, the agriculture opportunity here. And so it really, without all this, without the rocks, we just couldn't do all this. So thank you for those of you that have stuck around. You will not be disappointed in hearing about the rocks of Imperial County.
I'm probably the only speaker at this conference whose introduction will run longer than his presentation. As Charlene noted, and the advertisement noted, this is a workshop, so I'd like to sort of change format. I don't really have a formal presentation. This is intended to be an interactive workshop So please feel free to interrupt and ask questions, because people do that to me all the time, so I'm used to it. So if Connor can load up, I'm looking for it too. But I would tell an Irish joke in the interim, but I don't really have one, so. Oh, great, okay. Okay, so as the advertisement said, it's Geothermal 101. If you know everything there is to know about geothermal, this is not for you. You can start your weekend now. If you're interested in learning a little bit more about geothermal, then this is what the workshop is about. So we've heard an awful lot about renewables. A speaker earlier this morning mentioned that part of the early planning in the Imperial Valley had geothermal as the only renewable element. And of course, with the most recent run-up in interest in renewables, solar and wind have been very much in the news. And oftentimes it comes up, whatever happened to geothermal? I guess once you've made Fox News, you've really made it. But the answer is nothing. It continues to cook along and do just fine. It's been a very intimate part of the energy mix in the Imperial Valley. It represents more than 600 megawatts exported from this area alone, north of the border, and about 720 megawatts in Cerro Prieto. And it's been either explored or attempted to be developed in the Imperial Valley for more than 5 decades. So it's not exactly like it's a brand new kid on the block. So the question always becomes, what exactly is the new spur? Well, the advantages to renewables have been touted in a number of different talks at this conference. But the primary thing that spurred geothermal exploration is that maturity of the techniques. So what exactly do we explore for? We explore for heat. Everything else is pretty much the effect of heat. All the geochemistry, all the geophysics, all the other things that we try and search for, it's all the effect of heat. And that seems to be an easy proposition because the Earth is an active planet and it's always losing heat from the interior. And it's a very large resource for this particular planet. But the problem is that it's not evenly distributed everywhere in the crust. So as noted in this particular slide, the way that heat increases with depth is different for different areas. Using the United States as an example, the warmer colors here are a more rapid increase in heat as you go to depth. In this particular case, the scale is down to about 5 kilometers. And you'll notice some of the cooler colors, like here in the Sierra Nevada or here east of the Rocky Mountains, is a completely different increase in heat with depth. And a lot of geothermal exploration has focused in these areas where heat increases really rapidly with depth for an obvious reason. If you don't have to go to 5 kilometers to get out to 200 degrees C, then easily you can be accessing geothermal resources. A geothermal resource is a major thermal disturbance in the crust, and it's shallow enough to be accessible with conventional drilling methods and hot enough to be generating power at a very high level. Now, there are many, many different ranges of geothermal resources. It ranges from direct use applications to generating electricity. The main focus here is generating electricity, so we'll stick with that. So concentrating on those areas where high heat flow makes the temperatures increase rapidly with depth has been the sort of geothermal exploration pattern worldwide. A lot of those areas are at the boundaries of the Earth's major plates, and that's why exploration has been focused there. So a lot of the places that, other than the Imperial Valley that we talked about, are through Central and South America and Indonesia, the Philippines, and also the African Rift and central part of Europe. Some of the earliest geothermal developments occurred here in Italy in a place called Larderello. It's one of the longest running geothermal fields in the world. And it brings up the commonality to all geothermal systems. Every geothermal system needs a heat source, preferably a young heat source. It needs this clicker to actually work. It needs fluid, so hot water, and it needs permeability, the ability to move fluid through the rocks to mine the heat out of the rocks. Now, everybody out there who is a developer or a permitting person or a marketer will say, well, you also need a market. But as I said, this is a discussion of the geology and the exploration end of things, not necessarily the economics or the permitting or anything else. So I'm sticking to a topic that I know. So some definitions here. Young heat source, preferably less than 1 million years old. Now, remember, I'm a geologist, so for me, 5 million years is sort of like yesterday. For fluids, you'd really like them to be relatively benign. You don't want a whole lot of dissolved solids in them. You don't want a whole lot of production problems when you're in the process of trying to produce the resource. And permeability, as I said, cracks in the rocks, not necessarily porosity, but interconnected cracks in the rocks that allow the system, when it's heated up, to convect and mine more heat out of the rocks. So common technologies to produce this, like here in the Imperial Valley, are power plants that separate a small amount of steam from water. There are some exceptional systems, like the geysers and Lardarello in Italy, where you can utilize the steam directly from the ground and flow it to a turbine and generate electricity. That isn't necessarily the case in every geothermal system, because those steam systems are not as prevalent as hot water systems, where you can actually use some of the steam from the hot water to spin the turbine. An alternative technology is using a secondary working fluid like the ORMAT process and other secondary working fluid processes that mine the heat out of the fluid with a very low boiling point liquid and then use that to spin the turbine. And that type of technology is common to the developments at Brawley, Heber, East Mesa, places like that in the Imperial Valley. The United States has a very diverse set of geothermal resources, probably more diverse than anywhere else in the world. In this particular slide from the Department of Energy and USGS, all of the brighter colors are relatively high heat flow areas, like we talked about in that original slide of how fast does it get hot. And all of the cooler colors are relatively low heat flow areas. All these black dots that look like somebody took a shotgun and spread it at that map, those are all data points. So what exactly are we looking at here? Well, the current accounting has a number of identified resources, or at least installed capacity. That's about a little bit less than 3,000 megawatts. The identified resources on the USGS basis, where you could actually access those areas, and yes, these two colors do match the yellow and red parts of the map, totals up to be quite a bit more, almost 9,000 megawatts. But the total potential is in the range of almost 30,000 megawatts for all of the undiscovered resources and all those areas where newer technologies could advance the ability to produce the resources, or new exploration could be discovering new resources. So this is a graph that, or a chart rather, flow chart that everybody loves to hate. And I put it up because, I drew it up, and it illustrates a point that I'll try and make over time. But everybody from the permitting standpoint, the legal standpoint, the marketing standpoint, hate this, because there's a whole bunch of stuff in the background that they're doing to actually bring a geothermal project to the production stage. This is just strictly exploration, as I said. And so this is an exploration timeline over about a 5-year span of time. And the things that are highlighted here are the elements of exploration that a good exploration program goes through. It includes geology, geochemistry, geophysics, geothermics, heat flow in other words, and reservoir evaluation over this time span. So the numbers here also represent the amount of money that's invested in each one of those phases. Overall, for a total development of a project, historically, exploration, this stuff, has taken about 10% of the cost of a project. That varies a little bit depending on the project, but it takes about 10% of the cost. It all starts with geology, as Charlene said, understanding the rocks. It's very important to understand the geologic setting. It's very important to understand why the geology is giving you a heat source that'll fuel a geothermal system. So since we're looking for heat, volcanoes are an obvious bit of evidence of heat. It's kind of obvious, especially when they blow up in your face, like Mount Pinatubo, this last slide. Pinatubo is a little bit removed in the Philippines from a couple of major geothermal fields. But volcanoes in the Imperial Valley? What? Well, it turns out, yeah, not what, but yeah. Those 5 islands on the southern shore of the Salton Sea, Obsidian Butte, Rock Hill, Red Island, and Mullet Island, are all small volcanic domes. But they're not small in the sense of the total eruptive history of the Imperial Valley. They're just the most recent. Older geologic age dates for those domes had them probably about, say, 10,000 years old. Remember, we were talking about a very young heat source. Well, no, they're not. They're really about 940 BC from recent age dates. So they're very, very young. But there's been a lot of drilling to drill wells for, oops, nope, that's wrong. Can we go back? One more. Am I stuck? Can you go back, Connor? I keep thinking that I'm using a pointer, and I'm not. So the wells that have been drilled for these power plants have penetrated a significant section of the sediments in the Imperial Valley. And they penetrate some sediments that actually have a volcanic source. So there's been a constant volcanic history here in the Imperial Valley that shows that there's been a constant amount of magma, new molten material, placed into the crust. The question becomes why? Get ready, Connor. Soon. It has a lot to do with the evolution of the western margin of the North American plate. Now, plate tectonics is that concept that the Earth's crust is divided into 7 or 8 big crustal pieces that move and collide with one another and interact to form the geology that we have today. Where they're spreading apart or melting, we wind up having new magma systems in the crust. So, Connor, if you'll pay attention, if you will, to this particular area right in through here, because that's you. So as, hopefully, the North American plate evolves, Connor, you're the only person to stop plate tectonics, Connor. So you'll see here, this is the transverse ranges, and this eventually will become the Gulf of California. So the Imperial Valley evolved here as this system of rifting came on land. And that huge source of new magma and heat flow is directly related to the fact that the East Pacific rise has propagated right under the crust in the Imperial Valley. So this whole area from your section of the Imperial Valley to Cerro Prieto down here has a huge magmatic heat source over a long period of time. And that's extremely, extremely important in understanding the geologic setting of where we are and why geothermal resources are where they are in the Imperial Valley. And now I need to move on. So hot springs are also another evidence of heat at the surface, one of the most prominent pieces of evidence. And they're extremely important in figuring out the evolution of geothermal systems because we spend a lot of time sampling hot springs to determine the chemistry of the fluids that are being given to us for free at the surface. Why is that important? Well, here's a short graph of the chloride content in some geothermal springs, and the large column right here is ocean water. Ocean water is about 17,500 parts per million chloride. and a lot of other geothermal systems. Geyser in Iceland, no, that's not a typo. That's the way they spell it, and it's their word, so they can spell it how they want to. Waraki in New Zealand, Old Faithful Geyser here in the United States, Steamboat Hot Springs in Nevada, where Ormat generates about 90 megawatts, roughly the needs of the citizens of the town of Reno. Hot Bubbling Pool and Hot Creek and Little Hot Creek in the Mammoth Lakes area, and then some wells here, including Casa Diablo at Hot Creek, a steamboat well, and a well in New Zealand. So you can see that the chloride content of seawater compared to most of these not so briny systems is really quite high. But let's look at something else. This is silica. Same wells, same areas, same springs. And here is ocean water. Why? That's the question. What's the difference? What's the difference between all these waters and seawater? It's hot. Exactly. That sort of monotonic increase in concentration of some elements in geothermal water are exactly the reason why you can use geochemistry to do an awful lot of things before you've ever drilled a well, before you've done anything else. You'll understand a lot. You can calculate, or estimate, I should say, a temperature for whatever reservoir you happen to be searching for. You can say an awful lot about the area that a geothermal system might occupy. You can say a lot about the water's cold water interacting with warm water. And you can say something about, potentially, the types of fluids that you'll encounter at depth. Now, that's not to say that every geothermal system is, not very briny and not very corrosive and doesn't have a whole lot of problems. Because a lot of the higher temperature geothermal systems here, like the Salton Sea, are more than 10 times saline, the salinity of seawater here. And that causes problems. And geochemistry is key to handling those problems, because being able to produce the system and still keep it productive over a long period of time without having minerals precipitate out in the fractures that you depend so much on in the crust, or without having the minerals precipitate out in the pipes that you put at the ground on the surface, it's extremely important. And it's a geochemical question. So where are we in our exploration timeline? Well, we've gone through the geology, we've gone through the geochemistry here. A prospect remains a prospect as long as all of the information continues to be encouraging. And everything's been pretty encouraging through this stage. So now we're ready to take a look at geophysics that gives us some idea of what things look like in the third dimension. It's very important in that geothermal systems alter the rocks. All that heat, all that circulating fluid changes the rocks relative to all the other rocks around it. Changes the density, which is what gravity is important for. Changes the magnetic susceptibility, which means the magnetic conditions of a geothermal reservoir are completely different than the surrounding rocks. And it changes the resistivity, or specifically the conductivity. So you can use resistivity to map sort of where the alteration of the system is and how it's evolved over time. One of the most common techniques is an electrical technique called MT. I love this slide. It's really colorful. The Earth is a magnet, and a magnet spinning in an electrical field, specifically from the solar wind, generates a current. Those currents can be measured, and they're very convenient. MT is a very convenient way of doing it because it's not very intrusive, and you can do it over long periods of time. Long period MT studies actually have seen look at currents that go through the core of the Earth. And you can get it relatively inexpensively compared to a lot of other techniques. But the most important thing is it gives you an idea of how things look in 3 dimensions. This is not the Imperial Valley. This is a different area, the Medicine Lake Highlands in Northern California. But what's important about this is that the interpretive techniques tend to take a relatively one-dimensional view of the Earth and move it slowly into a 3-dimensional view of the Earth. So all of the resistivity pattern here, these are all wells or resistivity stations, MT stations, is related to all of the lower temperature alteration of the rocks at the top of a geothermal reservoir. And into a geothermal reservoir where these wells are drilled, the mineralogy changes decidedly to higher temperature, more ordered forms of minerals that aren't as conductive. So you're looking at a three-dimensional picture of how the system evolved. And you can take different cuts of this and see at different elevations how the system has evolved and what it looks like at depth. So we've done all the important geophysics. We've actually come to this stage of our timeline. We've spent probably in the range of several hundreds of thousands of dollars, but certainly nothing compared to what we're going to spend when we get into this geothermics part here. Now we're going to actually sample the third dimension. We're going to actually measure the temperature. And the only way we really do that is drilling. And generally it's done with smaller scale rigs, not necessarily a full-size rig, because these are not full-size holes. Some of the diameters of the holes, especially core-drilled holes, are only about 2 inches. So the only thing you're trying to do is you're trying to give yourself a tube down into the earth to measure the heat. Not necessarily for production, not necessarily for sampling, although, please, it would be great to have a geochemical sample, but it's not necessarily the purpose. So what do we wind up seeing? Well, a lot of that data is plotted on a temperature depth plot. So this axis is temperature in degrees C, and this axis is depth. And this little sort of rose diagram right here, you remember those lines that I showed, the red, yellow, green, okay, that's those lines. So along this line, things get hotter faster. For those of you who don't speak degrees C in kilometers, this would be like 20 degrees F per 100 feet, 10, 5, and 2, so on down. Obviously, your goal is to get hot fast. What is this line right here? Well, that's the boiling point depth curve for pure water. Since the circulating fluid, the working fluid in a geothermal system is water, you're sort of governed by the physics of water. And that's, think of it as the speed limit. That's as hot, as fast as you can go, as long as you're dealing strictly with water. And so here, at like a couple hundred meters, you might wind up being almost out, 175 degrees centigrade, or about 370 degrees F. That's one of the reasons why permitting agencies like the USGS and the BLM say, you know what, a shallow temperature gradient hole generally means something up here shallower than about 150 meters or about 500 feet. Now, that's a relatively easy thing to do, but it has your investors in Wowie Zowie Geothermal here ready to sort of put down a bid on a second yacht. They think this is going to be an easy deal. The boiling point depth curve, though, says, well, we're going to have to start shallow because every producing geothermal system pretty much follows that boiling point depth curve. And we're going to have to take it careful. The cheap part of a 500-foot gradient hole up here in this section is that you don't have to worry about blowout prevention equipment, even though, again, as noted, for a number of these geothermal systems, even at 100 meters, you can have some fairly high temperatures. You have to be very careful. So here we are. You're the geologist for Wowie Zowie, okay? And we're going to drill your temperature gradient hole program. So easy enough to permit. We're going to permit some 500-foot or 150-meter holes. So we rig up and we drill. What? Wait a minute. We're supposed to be over here, right? Not down here. Notice how this isn't really getting hot very fast. Your investors are having some serious questions about your geologic abilities. Show of hands. How many would drill deeper? Be brave. Come on. It's not your money. One person in the whole audience wants to drill deeper. All right, well, we do. You're the geologist in charge. Somehow you convince the management team that you really have your act together and you really know what you're talking about. So they give you more money, and they allow you to drill to about 300 meters, or about 1,000 feet. And now it's not working. There we go. They're much happier. Things are getting hotter faster. This is good, right? This is what you want to see. This is the exploration process. So now they're so happy, they say, okay, we're going to drill an intermediate depth program. We're going to give you money to drill in the range of like 2,000 feet, almost. Show of hands. How many would drill? Yay, all right, see. See how increasing, it's hotter, faster, right? That convinces you to, so we're ready to do it, okay? We bring in a bigger rig. We're ready to do it. We rig up and drill, and we wind up seeing that. What? What happened? Your investors now are really questioning your sanity. What is going on here? Why is this happening? Show of hands again. How many would drill? 1, 2, 2 brave souls. So you convince management, okay, smiling, whatever, taking them out to dinner, whatever it happens to be, you convince management that, yep, give me money and I will still, it's still a good idea. This is still a good prospect. So you rig up and drill even deeper. And what do you get? This is actually a true geothermal gradient hole that was drilled in a geothermal area in the United States. The lesson here is that you only know as deep as you go, or as well as you can interpret. That's part of the problem. That's part of the thing about looking through the glass but darkly. All of this stuff up here is all the interference with that heat flow signature that you're trying to get below. You're trying to get away from. All the things like cold water incursion, warm water out, cold water, well, actually no water table at all, warm water excursion, and cold water incursion. Every geothermal system exists because it's a balance between cold water influx and hot water outflow. And geothermal systems, because they, as I illustrated with resistivity and with geochemistry, because they deposit minerals and seal themselves off from the outside, they're separated from those cold water influences so they can exist. Otherwise, they wouldn't. Flooding them with cold water is catastrophic. So your investors now are extremely happy. They're buying that second yacht. So how do we put all of this together? This is a series of temperature depth plots, a bunch of confusing lines and everything else. Well, you try and put it together in a three-dimensional view, a conceptual model of a geothermal system. So you begin to piece it together just like we did with the geophysics. You take some slices for temperature. And from all of those elements, all of the things like alteration, the rocks, the temperature, you begin to develop a three-dimensional model of what the geothermal system looks like at depth. And from the geology, the geochemistry, the geophysics, and the geothermics, you begin to get an idea of where your targets are for rigging up and drilling a deep, true, full-size geothermal test. And that's the next step. Nobody's interrupted me, and I haven't had any questions, but we'll take a break for questions. No? No questions? I can't have explained myself that well. Okay, so next up, the thing about exploration, context is critical because geothermal systems are extremely variable. We have limited resource models. We have better resource models for paleo geothermal systems like ore deposits than we do for active geothermal systems because you can expose an ore deposit in 3 dimensions, they frequently are, and they're extremely well studied. So you have to figure out what you're testing. Are you just looking at anomalies? Are you looking at a resistivity anomaly, a temperature anomaly? Or are you actually testing a geologic concept? Everybody always asks, what's the most effective exploration tool? And the answer is, it's a well-trained geologist with a very well-constrained conceptual model. There is no such thing as a silver bullet. There is such a thing as a lot of hard work. And there's no simple formula. You don't really pick a single methodology. Context is important. and you're targeting the upflow zone, the permeability controls on a geothermal system, because that's what you're going to have to penetrate with a full-scale well in order to be able to produce the resource. And it's a progressive exploration setup where you go through all these phases in order to figure out a more and more detailed model. Despite the money that it costs, it's an exploration model that works. A question? The answer generally is no. And we'll go into that next, because next we're going to talk about discovery and development. So are there any other questions before we go on to, yes? Like? Generally, no. All of the plants that are built at the surface are engineered to withstand, under California code, are engineered to withstand a maximum credible earthquake. And in the Imperial Valley, that's pretty maximum. A number of earthquakes have occurred through the 80s and 90s along the Brawley seismic zone. There's been no interruption in production and no damage to the wells. It has the potential, but that hasn't been observed. All of the wells are completely cemented to the surface. So as long as the wellbore integrity is maintained, there's no possibility of the leakage of the geothermal fluids. Sure. Anything else? Next slideshow. So this is the chance if you want to leave now. There's a golf course out there. There's a weekend waiting for you. I always seem to stand, my presentation always seems to be before lunch, before happy hour, or before the weekend. And I don't really know why that happens, but so now we're at the stage to partially answer your question. We've reviewed the idea that what we're really searching for here is heat. And we've gone through the phases of searching and finding heat. So the question becomes, when do we wind up drilling a full-scale well? Well, part of it, too, is how much has it cost us so far, and what have we had to do for these different phases? Remember, we talked about a 500-foot or 150-meter hole. So the costs range from about $30,000 to $90,000. Why such a large range? Well, it depends on where you are, how much of this is road construction and site construction, and how much of it is environmental clearance and all the rest of that stuff. But you can do each one of these things and get to drill a 500-foot pattern of gradient holes relatively simply, because you're looking at 2 to 3 day completion times and relatively straightforward exploration. That's why a lot of companies like it. It's not that expensive. I know $90,000 sounds like a lot of money, but it's not that expensive. Intermediate depth holes are a little bit more complex, because a lot of times then you're looking at a little bit more environmental clearance. The BOPE here stands for blowout prevention equipment. And you're looking potentially also at targeting specific structures with an intermediate depth hole. And intermediate in this particular definition will say 300 to 1,000 meters, or about as deep as 3,500 feet. That's in partial answer to your question. That depth, does it just come down out of the, no. It has an awful lot to do with the geothermal setting, because you remember that example we did for Wowie-Zowie? Okay. If you're not deeper than 2,000 feet in that Wowie-Zowie prospect, you're not seeing anything. So it depends upon the geology. It depends an awful lot on the geology. It's extremely important. So that type of drilling is a little bit more complex. The blowout prevention stuff is, of course, to prevent those potential natural disaster problems that you might induce if you run into geothermal fluids shallow. And the timeline is a little bit different. You're looking now at about 10 times the time that it takes to complete a 500-foot hole. So it's a little bit more costly, a little bit more expensive, but well worth it, because you find out things exactly like that Wowie-Zowie case. And what you're trying to do the whole step of the way is develop a three-dimensional model of what the geothermal system looks like, what upflow looks like, and what outflow looks like. You're trying to think as deep as you possibly can. And sometimes conceptual models are just an image in a geologist's head, and sometimes they're fancy computer models. But still, it's always a conceptual model that drives where you're going and what you're looking for. So to get back to our timeline, to again answer part of your question, we're here now. Okay, we've done this. We've identified a prospect. There's nothing more that we can do to really improve our conceptual model. There's nothing more that we can do to really give us another clue as to where we want to drill and how deep we want to drill. We've got just about everything together. Right now, it's time to gut up and drill a well and actually see if we can discover something. So we're at this phase of the exploration timeline. So we rig up, drill a full-scale well. And after we're all done, it actually produces. Good. The investors had faith in you. You came through. So what does exactly that mean? What does a productive geothermal well mean? What kind of scale are we talking about here? Well, if you had a water well and it produced 200 gallons a minute in your backyard, you'd be very happy. You could take showers, run the dishwasher, even water the lawn. That's a good supply of water. It's really not that bad. If you had an oil well that produced 200 gallons a minute, if you had an oil well that produced 200 gallons a minute, we really wouldn't be having this conversation. Because that translates to about 6,857 barrels a day. Now, I didn't look up the price of oil this morning, but it's been fluctuating around $100. So let's just be arbitrary among one another and say that's $100 barrel oil. So you're looking at $685,000 a day, roughly about $2 to $3 million a year. You'd be buying us lunch. We'd be happy. But a geothermal well, you have to produce volumes of 2,000 gallons a minute, 10 times the productivity of an average good water well in order to have a successful geothermal well. And that's only a well. The next part of the program is doing it all over again, revising the conceptual model and drilling another well. And then you need another well. Why? Because you have to be able to identify a reservoir volume. If you had that oil well in your backyard, that's the only well that you need. In a geothermal system, you need a number of productive wells in a reservoir volume that you can produce a sufficient amount of fluid to actually generate electricity. So you need more than one well. And that's entirely before you've ever built a power plant at the surface. So that's part of the dilemma and the advantage of geothermal, because there's a comparative value of risk in different renewable technologies. With solar, wind, and geothermal, you're looking at the perspective of a number of different utilities, developers, and investors and financiers as to what they like and what they don't like about renewables. So there's some really profound differences in geothermal and in any renewable technology. You're trying to establish the resource quality. And there are always technology changes. There are always problems with capital costs and land needs, and there's some shared challenges like transmission access and credit markets and things like that. And we've been hearing an awful lot about those things, specifically at this conference this week. But the comparative renewable costs, geothermal is very competitive in terms of the acreage that it takes to develop, in terms of the capital costs, and in terms of the production costs. So it's a competitive technology financially. But a utility perspective is that it's, as you've heard several times from several speakers, that it tends to be a good base load generation source, something that utilities really like and really need. And that's something that almost all of the changing utility structure and many of the speakers that you heard at this conference have said, we've got to do this differently. We essentially have a grid that's about 75 years old, and we have grid management technologies that are about that old. So we need to do it differently if we want to use all these techniques. And renewable capacity, this has changed some. I apologize, this is a 2010 figure, so solar has definitely increased. But geothermal represents nationwide a part of the generation technologies, definitely not all, but a significant part. But did I miss one? Yes. One of the things about geothermal generation is that constant baseload power. It isn't the installed capacity. People quote large megawatt numbers, 330 megawatts of solar, you know, not to denigrate solar, not to denigrate wind or anybody else, but the actual time that it's online generating electricity in California, it's far outweighed every other renewable resource. Likewise, that capacity factor, the ability to stay online for long sustained periods of time without wild fluctuations in generation, is an extreme advantage to the geothermal business. And I chose this from CalISO for, let's see, what is it, March 12th? So 3 days ago. This is sort of the electricity usage, and you can go to the CalISO website and see this same graphic for every single day. So you notice, as again, a number of speakers have emphasized, here's the solar thermal peak, here's wind peaking in the evening, but here's geothermal, ticking along quite nicely, all day long, all night long. Good baseload power. And that's part of the contribution of renewable resources in California. This is load versus time of day. Load being exactly what the grid contribution is, how much the grid needs, that's that orange top line, and how much renewables actually contribute to it. And comparing that to solar and wind, you can see the decided difference, because they don't make up a large fraction of the total generation mix. They can in the future, they must in the future, because we have to look at generation and energy sources differently as time goes on. And we have to look at managing those energy sources differently. So one of the problems that has been emphasized in this conference is that those sources, wind and solar, have a tendency to have drastic excursions in their generation. It's not a criticism, it's just a simple observation, as the previous speaker talked about. You know, all of a sudden all the panels will go into stop mode. Well, for a utility, you have to understand what utilities want. The electrical system is built around the idea that there's a constant flow of electrons, that it stays at a certain level and you can ramp it up slowly and ramp it down slowly. But an excursion where all of a sudden an entire whole piece of your generation system says, oh, I'm going to sleep now, and it's going to be 15 minutes to a half an hour until I come back, that's not what a utility likes. It's not what a utility needs. In the past, some of you may remember the California great experiment of deregulating the utility market. There were manufactured excursions like that. A part of the generation system that was owned independently would say, okay, we're going to take this power plant offline, and then we're going to go back to the CalISO and say, yeah, you really need that power, because the CalISO is now screaming and saying, we're going to go into brownouts and blackouts. And so those people would call the CalISO and say, sure, I'll put the power back online for 10 times the cost. And the unfortunate thing about our current grid management and our ability to manage electrical generation is that now we're looking at making that as a systemic part of the system. We're looking at more wind, more solar, more things that are variable, and that makes those extreme variations a part of the system itself, something that has to be overcome and planned for. So the risks and challenges here, I won't insult your intelligence by making believe that you can't read this, but every renewable has its own challenges. And one of the primary challenges in solar is land use. Last year at this time when I gave this talk, there was an awful lot of controversy about one of the solar projects in this area and endangered species. So one of the things about solar is it's land use intensive. and you're looking at a desert environment where there are a number of endangered species that may be impacted. So that's a problem. It's a problem, a challenge for solar development. And geothermal risks and challenges, the ones that we've been talking about now, you know that 5-year timeline? Every investor hates that. They want to be able to do it now and get it online now so they can make money. But a 5-year development cycle is a relatively long timeline, especially if you're the person who has to pay all the money up front to get to that stage of actually having a successful geothermal well. They're large capital outlays, and these days, the financing hurdle is you have to have 75 to 100% of the resource proven before you can go to a bank and say, I want some money. If you don't have that kind of level of confidence, that kind of level of investment in already establishing that the resource exists, the bankers are simply not going to talk to you. And resource depletion. Why is it a renewable resource? Well, all geothermal systems return the produced fluids to the subsurface. You're using that working fluid to mine heat out of the rocks. And somewhere, depending on how you calculate heat capacity, 75 to 95% of the heat remains in the rocks. How long do geothermal systems last? Well, geologically, it depends. It depends on how efficiently you're removing heat, because all that convecting fluid removes heat very efficiently. So you can have a heat source, a magma body down here at depth, cooled off relatively quickly being, say, 50,000 years. Geologically, that's a very short period of time. But the thing about geothermal systems, especially from the background, as I said, of paleogeothermal systems, like mineral systems, is that you continue to have events that put new heat sources into the crust. Many of those systems have lasted for several millions of years. The steamboat system in Nevada has been an active outflowing geothermal system potentially for as long as 3 million years. So it's a long-term renewable. And especially if it's managed, you can continue to produce from those systems over a long period of time. So all the resource questions that we've been trying to answer to get us to the stage of actually generating electricity and building a power plant at the surface were all those exploration approaches that we were talking about before. We're trying to establish the temperature, the depth, the quality, the longevity, the size, all those things that we do with exploration. So to summarize, we're looking at discovery and development at the end of exploration, at the end of all that phased exploration program. We're looking at temperature permeability and productivity when we actually drill a discovery well. And over the long term, to verify the resource, we're looking at establishing how big it is, hopefully big, what its capacity is for production, and how sustainable it is over a long period of time. I appreciate the opportunity. If you have any questions, thanks. Yes. Well, if you think about it, if you're producing brine that's 250,000 parts per million, that means 25% of what you produce is not water. So essentially 25% of the resource is not accessible for generation. It's handled through a very delicate balance of a small amount of steam taken off and modifying the chemistry a little bit, and then putting it back down in the subsurface. I didn't show the cost of an average geothermal well in other places. The cost of a well would be, well, I don't know, yeah. A power surge, right? That was that solar, no. The cost of a geothermal well would be, say, it all depends on depth and time, but it would be, say, $5 to $7 million. In the Imperial Valley, you're looking at putting a 1 in front of that. So you're looking at an average cost of $15 to $20 million a well. Why? Well, a lot of the casing that you would conventionally use in the geothermal business, standard steel or alloy casing, isn't really usable here because the brines are corrosive and they simply remove it. They dissolve it. So you've got to use very special casing, and it's very expensive. A lot of it is titanium alloy, and it's extremely expensive. The length of a string, the length of a casing string, to get to the resource before you produce the resource is very expensive, which is why a lot of the early development in places like the Salton Sea were undertaken in the relatively shallower part of the resource and not the deeper part of the resource, because the investment in that specialized casing is extremely expensive. Yes?
We toured the Symbol Lithium facility
Yes.
in the field trip, and so not everyone would be on there and be familiar with, in that quarter of a cup of material in a cup of water, what potentially is in those solids in that cup.
The periodic table. You know, with salinities like that, seriously, you could produce the periodic table. A lot of things that have been attempted are recovery of base metals, recovery of precious metals. Lithium is a excellent recovery method. A lot of lithium mining is done actually as solution mining, where you circulate water through rocks that have lithium minerals in them, put them into solution, and bring it to the surface. So a geothermal system is essentially giving you that. In the Salton Sea, Brawley geothermal systems, that's exactly the case. Now, one of the things that occurs in a lot of projects like this, historically, at least my observation, a lot of the things that we heard talked about today, let's do this with it, let's do solar, let's do, salt ponds. Those are all things that are excellent second stage to a resource. Producing minerals from the resource is another second stage, but the initial development of almost all the geothermal resources in the world, and in the Imperial Valley too, focused on one thing and one thing only. Let's generate power, let's do that first, and let's take all the rest of these things later. But yeah, it's definitely something that should be done.
Sir?
Yes?
My question may not be, this not be the right place to ask the question. I will, but I cannot help it. Keeping warm is a big challenge in some parts of the country in the winter. And in some of those places, the word geothermal is often used as an adjective, like to modify domestic water heating or domestic heating, etc. And I know people who are very successful in using geothermal domestic heating in the Midwest, for example. And I know other places have failed catastrophically. And I cannot imagine doing all of that kind of deep testing in order to figure out what the temperature gradient is, etc. Are there any rules of thumb that people can use to figure out if something like an investment like this would make sense to keep warm, or?
Yes. A lot of the economics of direct use that I mentioned as one potential use of geothermal energy is related to being able to install it before you build the facility, not after. Retrofitting is one of the bigger economic costs. And there are many, many areas, especially geothermal areas, where that cascaded use of the heat is very worthwhile. One of them is Iceland. Iceland is one of the greenest countries on the face of the earth, and there's a classic slide that I often show in another type of talk, where the city of Reykjavik used to generate all of its electricity through diesel barges offshore, and it's just like this huge layer of smog in 1930 that's obscuring the city, and now there's none of that, because they use all of the heat from the geothermal system before they return the injected fluids. So buildings, facilities, everything is geothermally heated, and it's an extremely green environment. And it can be done in a number of different places. Ground source heat pumps and direct use applications are very worthwhile. The problem is that, just like with current electricity generation, we tend to look at things that have the lowest capital cost and the lowest installed cost. And that's the only factor that we factor in. In geothermal, you're sort of to twist the term a little bit, you're sort of paying for all the fuel up front. So that's a large upfront capital investment with direct use. But it is very much more logical. If you think about thermodynamics, what we do to heat water is ridiculous. We burn carbon fuels at several thousand degrees to heat water to like 120. That's really kind of crazy if you think about it, because there are many other ways to do it. We just don't have to burn those fuels to do it. I don't know if that answered your question.
Thank you.
I appreciate the time. Thanks.
Well, ladies and gentlemen, thank you for staying. This ends our summit. And so we will have all the PowerPoints on the Ivy EDC website. Allow us a few days to get those up, but so sometime late next week you should see them on there. So if you'd like to get those and see them again. Thank you for your attendance. We look for you next year. And so have a great weekend. Thanks.